All right, guys, this is note card 7, number 7. It's called the intermediate value theorem. And in parentheses, it says number 1 of the big 5. In calculus, there's 5 big theorems that you have to know and you have to know well. So the intermediate value theorem, sometimes it's just simply called the IVT. Okay, so let's read what it says and then I'll try to give you a graphical way to think about it. So it says that intermediate value theorem, or IVT, is an existence theorem which says that a continuous function on an interval cannot skip values. The IVT states if f is a continuous function on the closed interval a to b, and if k is any y value between f of a and f of b, then there's at least one number c in the interval a to b so that f of c equals k. That's a whole bunch of complicated math speak for the following. Okay. Now let me just draw a graph to help you understand the IVT. So here's a better way to think about the IVT. All right, so let's say I have some XY graph. Let's say we have some function, and we'll call that f of x. Well, if we narrow into this function, let's pick two x values. Let's call that a, and let's call that b. So a and b are just two x values. Well, for this x value of a, it has an associated y value. Okay, there's a point on the graph. So we would call that f of a because it's the function of value associated with a. And the same thing here. For this x value of b, it's defined on the graph, and it also has an associated y value, which we would call f of b. Now, here's what the intermediate value theorem does for us. If I have some y value, which we're going to call k, as long as this function is continuous, which it is, okay, I can draw this function without picking up my pencil, so it is continuous. If there's a certain y value, which we're calling k, that's between f of a and f of b, okay, if we take this over, then the intermediate value theorem says that as long as the y value here is in between these two y values, then there's got to be, it has to come from some number c that's between a and b. Okay, because here, this k, f of c equals k. Okay, when the x value is c, the y value is k. So again, if the function is continuous, all right, and you look over an interval between a and b, all right, if you got a y value in between the two associated y values, then there's got to be an x, it has to come from an x value that is somewhere in between a and b. Okay, that's what it says. That's what it says. All right, now it also does one other thing for us. Okay, there's one other important point about the intermediate value theorem. All right, as long as the function is continuous, there's a certain range of y values. If you can see it here that I'm trying to draw in. Okay, do you see how I kind of made a little squiggly line between f of a and f of b? Those are all the y values between f of a and f of b. If you notice here, every y value between f of a and f of b gets hit at least once. Okay, these all come from different points along the graph. Now it can get hit more than once. I mean, some of these hit the same numbers. But another important point about the intermediate value theorem, kind of a corollary to it, is that as long as the function is continuous, every y value between f of a and f of b, like let's say that was 5 and that was 10, every number between 5 and 10 will get hit. So 5.01 gets hit, 5.02 gets hit, all the way up to 9.999, all the way up to 10. So every y value between 5 and 10 is also going to get hit there in that case. Okay, so that's an important aspect of the intermediate value theorem. So let's look at some of these problems. Okay, it says use the intermediate value theorem to show that f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. Okay, well, what the heck are they talking about? And what is a 0? Okay, a 0 is where it crosses the x-axis. So just to kind of help your understanding out here, let me go ahead and put this function into my calculator. So x cubed plus 2x minus 1. All right, and let me just do a zoom standard so we can start to see that cubic function. Kind of looks like one of those. Now, we only care about that function over this interval. And this interval are x values. Okay, so I'm going to change the window here, and I'm just going to look at the function between an x value of 0 and an x value of 1. Now I'm going to hit graph again. Okay, there it is. There it is. So let me kind of just draw that graph or draw that shape. Kind of looks like that. I'm just making a copy of it. So that's an x value of 0 right there. And here's an x value of 1. Okay. Well, let's ask ourselves, is the function continuous over this entire interval from an x value of 0 to an x value of 1? Yes. So what we would say f of x is continuous on the interval 0 to 1. Now, why is it continuous? How do I know it's continuous? Let's say I didn't make the actual graph. Because f of x is a polynomial, and polynomials are continuous everywhere. So what I did here, I checked the first condition. Okay. Now, what do you have to do in the second condition? Well, I have to show what the y values are. Okay. So I have to tell the reader what's that y value and what is this y value. Okay, well, how do you find those? Let's say I didn't actually draw the graph. Well, let's figure out what f of 0 is. If I do this algebraically, I'm just going to plug in 0 everywhere I see an x here. So 0 cubed, that's 0. 2 times 0, that's 0, minus 1. So f of 0 is negative 1. So this right here has a y value of negative 1. Now let's do the same thing for f of 1. Okay, and let's figure out what the y value is here. Alright, so I'm going to do 1 cubed, that's 1, plus 2 times 1. 2 times 1 is 2, and then minus 1. Okay, so if I do some simplification, 1, negative 1, that's 0, plus 2 is 2. So I figured out what the y values are. But what's the k value we want? Well, the k value we want they tell me is 0. Okay, because that's the definition of a 0. Okay. So what I would say here, I would say that -1 is less than 0 is less than, I should be less than or equal to, sorry. Okay, 0 is in between these two other y values. This 0 in green is between these other two green values. Okay, so f of 0, that's what -1 was equal to, is less than that k value, which was less than the function value at 1. Okay, so it meets the second condition. 0 is between these two values. Okay, and I showed that through calculations. All right. Now, as long as 1 and 2 are true, okay, then I can say something like this. By the intermediate value theorem, there is a value which I'm going to call C. Okay. It's an x value. Okay. There's the x value of C in the interval between 0 and 1 such that so I'm just saying there's an x value C in the interval 0 to 1 such that f of C, okay, what does this represent? That represents the y value equals 0, the same number as that. Okay. So, quick review. All right. The intermediate value theorem is going to work because this function is continuous and the y value I care about, 0 in green here, is between these two. And as long as 0 is between those two values, as long as the function, the value we care about is between those two values, there's got to be an x value in the interval 0 to 1 so that when you plug in this x value that you're calling C, you're going to return the y value that you care about. So if I kind of look at the graph, okay, it's right there. And my calculator, I can actually calculate what that is using the 0 feature. And it's 0.453. Okay, so here, C is roughly equal to 0.453, which is true. C is a number between 0 and 1. 0.453 is between 0 and 1. Okay, now, even if we couldn't use our calculator on this question, you couldn't actually figure out what the actual value was, but the intermediate value theorem assures us that there is a number C in that interval, 0 to 1, that makes it work. Okay, so let's read the next problem. It says, a car travels on a straight track. During the time interval between 0 and 60 seconds, okay, so this part, we do have a table here below. Those represents the times, different times. So during the time interval between 0 and 60 seconds, the car's velocity, v, it's measured in feet per second, is a continuous function. So they're telling me that the v curve, the velocity curve, is continuous. The table below shows selected values of the function. Now it says, for the time interval between 0 and 60 seconds, must there be a time when the velocity equals -5? Justify your answer. Okay, so let's think about this. Okay, so they're asking me, must there be a time when the velocity equals -5? So when we look down here at the velocity values, we don't see anywhere that it says -5 directly. But will the intermediate value theorem hold here? Well, let's think about it. Okay. Does it meet the conditions? So is v of t continuous? How do I know that v of t is continuous over the time interval 0 to 60? How do I know that? Well, it tells it to me in the problem. So I know that v of t is continuous over 0 to 60 because it is stated in the problem. Okay. So now let's check the second condition. What are the y values? What are the velocity values? Well, over this time interval. Well, what's v of 0? V of 0 is negative 20. I get that from that point in the table. What is v of 60? Well, that's a value of 10. Okay. Now, they're asking me, am I sure to get a velocity value of negative 5? Is this number definitely between these two somewhere? Yes, it is. Okay, so negative 20 is less than or equal to negative 5, which is less than or equal to 10. So here the velocity at time 0 is less than or equal to some k value they gave me, which is less than this. So the first two conditions are met, which means that it has to be true. Okay, it has to be true. So in part 3, we just say by the intermediate value theorem, or by the IVT, there is a value c in the interval (0 to 60) such that the velocity at time c equals negative 5. And you could even narrow it down further than that. During what time period does it actually have to be? Is negative 5 between these two numbers? No. Between these two? No. Between these two? No. Between these two? No. But between these two values, negative 5 would exist. So I could have even narrowed it down further. All right, actually, I'm guaranteed sometime between 35 and 50 seconds to get a velocity value of negative 5, because negative 5 is in between these two values. Now, it could happen in other places. Okay, it could happen in other places, but I'm guaranteed to get at least one in that time interval. Okay. What do I mean about there could be more than one? Let's think about this for a second. So kind of that second part of the intermediate value theorem, okay, going back to that curve, like if this is your A value, then that would be the F of A value, all right, and this is the B value, and this would be the F of B value. Okay. All right, so kind of going back to that a previous example, let's call that 6 and let's call that 12, and let's call this 3 and let's call this 4. Okay. So as long as this function is continuous, let me just draw it in here. Let me draw a crazy graph. Let me kind of just draw this graph. All the intermediate value theorem does for me for sure, I know that I'm going to get every y value between 6 and 12. Okay, I'm going to get a y value of 6, 6.01, 6.02, all the way up to 12. I know that for sure. You see, all the y values there get hit. Let me just kind of extend this line a little bit. Okay. You notice they get hit here again, and they get hit a third time again here. So like, is there a time for sure, or what about, can I know for sure that I'm going to get a y value of 9? Let's say that's a y value of 9. Yeah, I am. I know for sure I'm going to get at least 1. But in this one, there's actually multiple c's. Okay, there's different c's that work. Now, could I get other values between, like other than numbers between 6 and 12? Yeah, you see here, it goes above 12 for a certain amount of time in that interval. It goes below 6 for a certain amount of time. Okay. But I'm not guaranteed numbers above 12. It doesn't have to do that. I'm not guaranteed any numbers below 6, but we still could get them. All right. So if you kind of think about these numbers, I'm just going to go ahead and plot out some of these numbers so you can understand it a little bit more. Okay. So here's the values of the velocity, and here's the different times. Okay, so if we look at the table, at time 0, we got a velocity value of -20. So when the x value was 0, the y value was -20. Okay, if I go out to 15 on the table, when the time is 15, the velocity is -30. So that would be that point. All right. When I go out to 25, a time of 25, it's -20 again. If I go to 30, a time of 30, it tells me it's -14. I know my scaling's not perfect here, but you're getting the idea. At time 35, the velocity is -10. At 50 seconds, my velocity is 0. And at 60 seconds, the velocity is 10, positive 10. Okay. We do not know what happens in between these points. All I know for sure, the graph can do crazy things, but all I know for sure is that I'm going to get y values. I'm going to hit every y value between -20 and -30. It could go up to -5. Okay? It could do something like that, but we're not guaranteed that. All we're guaranteed is to hit every y value just between -20 and -30. That's all the intermediate value theorem says. We could get numbers higher than that or lower than that, but I'm guaranteed to hit it here. Okay. Same thing between these 2 points. Okay. So the graph could do crazy things. Okay, it could just be a nice curved portion, and I'm guaranteed to hit all the y values between -30 and -20 again. Then I'm guaranteed to hit all the y values between -20 and -14. It could go higher than that, or it could go lower, but I know for sure that I'll get every y value between there. All right. And then if I just keep kind of going between points here, okay, I just have to make sure it's continuous. How do I know for sure that I'm going to cross -5 at least once? Okay, it could cross more, but the reason why I know it's going to work, the velocity is going to equal -5 somewhere in that time interval, okay, is because the graph started at a y value of -20 and it ended at a y value of 10. And -5 is numbers in between -20 and +10. So I'm guaranteed to find at least one value that works. Okay? In this case, there's got to be at least one value between a time of 35 and 50. Okay? Because those are numbers between -10 and 0. It could happen more than once. Okay? It could happen 1,000,000 times. It could happen 100 times. But I'm guaranteed that it happens at least once. All right. Now, why does it need the first condition? Why does the IVT need a continuous function? Okay, so if we kind of think about the same example, if the function wasn't continuous, let's kind of make a dashed line at -5. All right, maybe it started down here at -20 and it ended at 10 here before. If we didn't have the continuity piece, the graph could kind of go like this. All right, let me draw a function that's almost continuous but not quite. What about if we got a circle right there? Okay. On this velocity graph, there's no y value of -5. It could be an open circle. So that's why we need the first part. That's why the graph has to be continuous for the intermediate value theorem to work. So guys, that's that note card. If we look at the packet tonight, you got some more practice here about evaluating some limits, okay? But the real piece of this content, the new content, the intermediate value theorem, applies to these problems here, 11, 12, 13, and 14. Those are the intermediate value theorem problems, okay? The rest is just review practice for you, okay? And then on the back, there's some more practice with the intermediate value theorem. We want you to do the whole packet. That's just a good cumulative review so far about limits. But the pieces that involve the intermediate value theorem are these problems, 11 through 14, and then these problems down here on the back of it. Okay. So that's your packet tonight. Just give that a shot. Thanks for watching.